My original idea for this project was to make a machine that swings a sword and cuts a watermelon, but if it's worth doing, it's worth overdoing. So I decided to make the sword as well. Unfortunately, my forge does not quite get hot enough to make a larger cutting edge.
Hello, this is Nathan George. That's Dr. Nathan George to you, and today we'll be conducting our experiments on using blacksmithing tools. Alright, as we see, he has made himself a little forge and stuff, and he's gonna try to blacksmith. But again, this is very dangerous. Let's see what happens. Hey Sugar, what are you doing over there?
As I said before, my forge was not sufficient to forge this piece of steel rebar. However, I was still able to forge a 2-inch cutting edge. I assembled the pieces of wood with some screws and nails. However, because of my construction motto, cut once, measure 0 times, the steel rebar's handle was too long, thusly the blade could not swivel properly. Cutting steel is not the easiest of things. Enjoy Nathan screaming in the background, and especially my facial expression. Angle grinder!
Wow. What are you doing?
I'm going to put an elastic here to hold them.
Noise. Oh, so it can like sling?
No, because this thing, they want to go out, and that causes more friction. Like, look. And if I,
Wait, how? Isn't it gonna slingshot down?
yeah, with my air cannon.
Yeah, but
The air cannon's going to lie right here, and the nozzle is going to be right there, and then we're going to pull on the valve, and it'll go.
I thought. Yo, Sugar, what are you doing?
Well, I'm just pressurizing the pressure chamber that's going to activate this decapitation device. As you can see, well, you can't see, but basically if you watch, when I open this valve, a lot of air pressure is released. And that's what's going to
And
happen.
we're gonna cut that watermelon. Watermelon. Cutting
I'm
watermelon.
going to charge it to 180 psi. Alright. Testing in 3, 2, 1. It doesn't sound like it should. It doesn't sound like it should because I lost most of the pressure during a valve malfunction. Also, notice how I fitted a piece of wood onto the end. Theoretically, this should increase the surface area, consequently increasing the force the air can apply. Oh, didn't open the valve properly. Or did I lose all the pressure? Yes, I did lose all the pressure. My safety precautions went out the window for this final test. Fire on the hole. This is 180 psi. 3. System may fail at any point, I might add, so this is particularly sketchy. 3, 2, 1, fire. Hey! Yes! We have complete perforation, folks!
The perforation is there.
Now, that may not have gone through the entire watermelon,
Let's celebrate.
but that's because I could only forge about 2 inches of edge by myself. But that is a conclusive test.
It's because he's a rookie, man.
As
He's
we
only
can
a
see,
rookie.
The watermelon has a clean cut going all the way through it.
Let me see.
It did a little more damage than I initially thought. As we can see, the watermelon can be very easily ripped in half. And as a celebration, I'm going to feast. And that concludes this experiment. Now for some boring physics stuff. End it. In order to solve this equation, I will be using the fluid dynamics equation. The force of drag equals 1/2 P times V squared times CD times A, where P equals density of the fluid, V equals speed of the object relative to the fluid, cross-sectional area is A, and CD is the drag coefficient. To solve for velocity, I'm going to find the speed of the fluid relative to the object instead of the speed of the object relative to the fluid. In order to solve for the velocity of the air, I will be using the equation V equals QA over R squared times pi, where QA equals the airflow in rate per second, R equals the radius of the inner pipe, and pi is the constant pi. In order to find QA, or the airflow rate per second, I must first find the volume of unpressurized air, or air at atmospheric pressure, that flows through the nozzle, and I must also find how much time it takes for this much volume to flow through the nozzle. In order to do this, I will be using the equation VA equals PC times VC divided by PA, where VA equals volume of gas at atmospheric pressure, PC equals compressed pressure, VC equals volume of pressure vessel, and PA equals atmospheric pressure. I calculated the volume of the pressure vessel to be approximately 1,737.7 cubic centimeters. The pressure in the pressure vessel was 180 psi during the final test. Standard atmospheric pressure is approximately 14.7 psi. I now have everything that is needed to solve for the volume of gas at atmospheric pressure. After running the equation, I found out that inside the pressure vessel, under pressure, there is approximately 21,277.9 cubic centimeters of air. Now, in order to solve for the velocity of the air coming out of the nozzle, I must find the air flow rate per second. The air flow rate is equal to the volume of gas expelled from the pressure chamber over the time it takes to expel this pressure. Using the editing software, I was able to determine that it took approximately 0.1 seconds to expel all of the air from the pressure chamber. Therefore, the flow rate is equal to 212,779 cubic centimeters per second. I now have everything required to solve for the velocity of the air coming out of the nozzle. It is 212,779 over 1 million, because there are 1 million cubic centimeters in 1 cubic meter, divided by 0.075 squared times pi. Therefore, the air velocity is 1204.08 centimeters per second, or 120.4 meters per second. Now we can use our force of drag equation. The equation is now 1/2 times 0.00129 times 120.41 squared times 2.1 times 0.005, where 0.00129 is the density of air, 120.41 is the velocity of the air next to the object, 2.1 is the drag coefficient of a rectangle, and 0.005 is the cross-section surface area of that rectangle. The result of this equation is a measly 0.1 newtons. I think we can all agree that the force applied to that sword was far greater than 0.1 newtons. So where did we go wrong? Well, in my opinion, there were two main assumptions that caused the inaccuracies of my calculations. These assumptions are that the gas coming out of the pressure chamber was able to completely depressurize itself before it hit the drag block. If the air was not able to completely depressurize, then it would be a far greater density than that of normal atmospheric air. This is surely the case given the distance that the nozzle of the pressure chamber was away from the drag block. The other more important assumption is that the calculation I used is really just a wind drag calculation, as if the pendulum or the drag block was just sitting in an air chamber getting hit by air that's going 120 meters per second. Whereas in this case, there was really an explosion that propelled it, and it was really more pressure than just air friction that made it swing around the pendulum as it did. So we're going to have a little physics bonus here. A great example of Newton's third law. If you watch the pressure vessel closely, you can see that it recoils away from the pendulum as it fires, which is equal and opposite reactions.
Why don't we have Wu-Tang in the background?
That's what it should be like.
Punk, you playing me, chump, you get jumped. Woo, it's coming through at a theater near you. And get funk like shoot.
Alright, fuck it, I'm gonna do 180 again.